Hi all, welcome to today's lecture. In this video, we are going to see how to solve a type 4 partial differential equation. When we have equations involving the variables x, y and the partial derivatives p and q, we call that particular form as type 4 PDE. Let us now see the procedure how to solve such equations. When we start the process, let us first separate the equation as p and x to one side and q and y to the other side. And since these are independent variables, both of them will be equal to a constant. So let us call the constant as a. Mark this as equation 1 and get the values of p and q from this equation 1 and substitute them in dz formula. Now here we have dz equal to p dx plus q dy. How do we get that? Let us see. Yeah, we know z is a function of x and y. So usual notation dz is equal to, through our usual partial derivative and total derivative relationship, we have dou z by dou x into dx plus dou z by dou y into dy, since z is dependent on x and y. And what is dou z by dou x? That is our the notation p, and dou z by dou y is q. So that is why here we have dz equal to p dx plus q dy. And integrating this equation both sides, we will get the complete solution. Let us see some problems now. Look at the first one. Solve p minus y squared equal to q plus x squared. And when you observe this equation, what are the variables and the partial derivatives involved? Yeah, it has x, y, p and q. So we can segregate p and x to one side, q and y to the other side like this, and we can call them as a constant. So since it is of this form, like a function of p and x and a function of q and y, both are being equal, we say this is type 4 partial differential equation. And let us see how to solve this now. From the separation, we can get the values of p and q. So since we had p minus x squared equal to a, from there we have p equal to x squared plus a. Similarly, the value of q will be a minus y squared. And these values of p and q, now we should substitute in the formula of dz. As we had seen, dz is p into dx plus q into dy. So we have dz equal to, what is the value of p we got? X squared plus a. And value of q was a minus y squared. Now let us integrate this equation. So when we integrate this equation, we have integral dz equal to integral of the right side. When you look at this, now it's a simple polynomial, x squared, a minus y squared, everything. So like with just direct integration, we will get z equal to x squared when we integrate x cubed by 3 plus a when we integrate we get ax. And in the second integral, a when we integrate with respect to y, when we do a into y minus y squared when we integrate y cubed by 3 plus of course c. So we get the complete solution. Again, remember what is the complete solution? When a solution is having just two arbitrary constants, it is called a complete solution. Let us do another problem. Evaluate the complete integral of p squared plus q squared equal to x squared plus y squared. Complete integral is nothing but the complete solution itself. Now consider the given equation. Now, as you observe, like here again, we have these four characters like p, q, x, and y. So we can segregate as p and x to one side and q and y to the other side like this. And we can call that as, instead of a, here we can mention as a squared, because it will be convenient for us to integrate. And as you observe again here, it is of the form a function of p and x equal to a function of q and y. So it is of type 4. From the equation what we have segregated, let us find the values of p and q. So p squared minus x squared was a squared. So the value of p is root of x squared plus a squared. Similarly, the value of q is root of y squared minus a squared. And substitute these in the formula dz, which is p dx plus q dy. When we substitute, what we get? Yeah, dz is equal to the value of p is root of x squared plus a squared into dx plus the value of q is root of y squared minus a squared into dy. Now let us integrate both sides. We have integral dz equal to integral root of x squared plus a squared dx plus integral root of y squared minus a squared dy. Do you remember which integration formula we need to use for such terms? Let us have a glance. Yeah, integral root of x squared plus a squared dx will be x by 2 root of x squared plus a squared by 2 sine h inverse x by a, which you would have studied in integral calculus in your previous semesters. Similarly, root of x squared minus a squared dx, that integration is x by 2 root of x squared minus a squared by 2 cos h inverse x by a. Of course, you have another equivalent formula in terms of logarithm for this, that also you can use. So integrating that, on either side we have integral dz, on the left side we have, so that is going to be z, which is equal to integral of the first term is given by the first formula, and integral of the second term is exactly by the second formula, but of course we have to change the variable in terms of y, which is the required complete integral. Now let us see an example of a partial differential equation applied in the medical field. Consider this problem. The dissipation of heat in the human body assumes a potential flow for the blood within the various tissues, including the tumor cell, that leads to a bioheat transfer equation. When you look at this equation, it is a partial differential equation, and the question is to evaluate the temperature of the tissue, capital T, which is a function of x and t. So before moving on to the exact mathematical formulation and the solution, let us have a glance of a heat dissipation in the human body. Actually, in human body, in various forms, heat dissipates, or a man loses heat through sometimes through radiation, or sometimes through sweating even, and through conduction, that when we wear wet cloths also heat dissipates. So these are various reasons, but when heat dissipates, we need to control the heat dissipation, because it affects the blood flow within the tissues, especially when it flows along the tumor cells, etc. So controlling this heat dissipation is really a necessary one, and this is a very classic example here, given bioheat transfer equation, and we need to solve using the partial differential equation techniques. Let us now move on to solve that bioheat transfer equation through our partial differential techniques. So look at this equation, dou t by dou x whole square, t into 1 plus x squared equal to dou t by dou t x squared. Here capital T represents the temperature of the tissue at time t. Let us compare this with our original notation z of x comma y, because we are very comfortable and convenient in using our usual notation p small p and small q. So let us relate this to the original variables. So comparing this capital T with z and x comma t with x comma y respectively, we can convert that given equation into our form p squared y into 1 plus x squared, which is equal to q into x squared, because what was p? Dou z by dou x, and q is dou z by dou y. So we have a partial differential equation like this here, and when you look at this equation now, we can segregate p squared, p and x to one side and q and y to the other side by doing like this. So that is divide by y into x squared on both sides. Then we get like this. So look at this equation. Is it not of the form like a function of x and y equal to a function of q and y? So that is our type 4 PDE. And we can equate these two to a common constant, say a. From that, we will get the values of p and q like this. P squared will be ax squared by 1 plus x squared, and q will be a into y. And taking a square root, the value of p is root a into x divided by root of 1 plus x squared, and of course q is a into y. Now substitute this in the formula dz, which is equal to p into dx plus q into dy. When we do that, we get dz equal to, in the place of p, substitute the value of p, and in the place of q, substitute a into y. Look at this. This integration doesn't seem to be very simple, but we shall use a technique to integrate this. Do you remember? Yeah, we can use a substitution method. So consider the first term, especially on the right side, for which we need substitution method. What is the technique of a substitution method? Usually, we replace a complicated term to a simple term like this. So that 1 plus x squared, let us replace as another single variable t. And when you differentiate this, we get dt equal to 2x into dx, or x into dx can be written as dt by 2. So the first integral becomes, I am just taking the first term alone, and let us finish that integration. So this is our first term, and it becomes now root a, we have taken it out, integral x dx. And now look at the numerator, we have x into dx, which can be written as dt by 2 into root of 1 plus x squared. We have that 1 plus x squared we have substituted as t. So we have by root t. Now taking this root t to the numerator, it is t power minus half. And t power minus half, when we integrate as our usual formula x power n, when we integrate we get x power n plus 1 by n plus 1. So using that formula we get t power half divided by half. So it is root a into root t, because that 2 into half will be cancelled, which is equal to, now you can replace back your t as 1 plus x squared. So this is the answer of the first integration. So let us now go to that equation 1. When we integrate, we get z equal to, integral of the first term is going to be this answer, and in the second one we had just a into y. So that when we integrate, now we will get a into y squared by 2 plus c. So which is the complete solution, but we shall change the solution in terms of the original variables, capital T, etc. So we have the answer of capital T as the root of a into 1 plus x squared plus a into t squared by 2, replacing the z as capital T and y as small t. So this represents the temperature of the tissue. So I hope all of you would have understood the techniques of solving a type 4 partial differential equation. So try to solve these problems. In this video, we have learned how to solve a type 4 partial differential equation. And in the next lecture, let us see about solving type 5 partial differential equation. Thank you all.